Hello everyone. Okay, we are going to do lab 4 integrated into the IOLab system today. Like we are not, it will be an instructional video, not a complete video like doing everything, but more of instructional. How will the graph look and how to explain the concepts. Okay, so let's just start. We are doing into lab 4. They have been written in Portland State University, University of Oregon, Seneca. Okay, so let's start the lab. So this is force and motion. You may write your name and state. So objectives will go to them. We'll be using force sensor, measuring the forces, scaling like how can we scale the forces, and we'll see the relationship between the force applied and the acceleration. Okay, write your name. Okay, and then click on go next. And you can write your name, save and go next. Do not forget to click on save and go next. Okay, so measuring forces in the investigation, we will explore the concept of constant forces and the combination of forces in one dimension. You can use this concept. So you can save and go next. Okay, they have asked you to use the robots. Okay, and then using the robots, you can scale the force like to a standard length. Okay, we are asked to like use the robots and then set to a standard length. Means we will fix it some standard length and set to that length. Okay. So there was access to start with one rubber. So you can take anything fixed, okay? So there you can I just use this one and then so that's before we go. Okay, and then keep like this, yeah. I want you to do with okay. So standard length we are keeping it. I'm giving it 10 centimeters, okay? You may keep it 15 also, but don't go too far because when you have to pull 5 you might be. So just 10 centimeter only. So let's take its length start from here. Okay, well, just the length of the rubber, standard length of the rubber only. So bring it from here and to the 10. This is 10 centimeters from here. Okay, just the rubber is just 10 centimeters. So they want us to do the standard length. How much? You can take 15 centimeter ratio to it. Okay, 5 centimeter. I don't think that's going to be a little less, but you can take 15 also. You can put the value here. That is one is of two. So after that they want us to use the two of them. Okay, two of them. Okay, and then and then it stays to the same standard length. Okay, like 10 centimeter was there to the same standard length and feel the difference. Like feel you have to feel it. Okay, and you go ahead, write your answer and click on save and go next. Do not forget to write before clicking on save and go next. Okay, in the next one, how large is the pole? So they want us to compare what you did. Okay, so how was the pole compared by the two robots compared to that of one used to only one robot? Okay, to the same standard length. So is it larger? It is actually twice. So how did you feel? Okay, then they want us to repeat the same thing using 3, 4, and 5 robots. Like keep it parallel, pull it. Okay, with 3, with 4, with 5, and but to the same standard length. Okay, like you have to make it. If you made it 10 centimeter for one, do 10 centimeter all. Now, suppose you set the rubber band to your standard length by pulling on it. Now you want to create a force 6 times as large. How could you create a short force? We did it 8 by 5. Yeah. So if you we were able to create around 5 times around. Now, if we want to create a 6 times, so you need to have same identical rubbers, 6 of them, it's just to the same length. Yeah. So that's the concept. The force could be scaled by screwing the rubber. Okay. Suppose you applied a force resistor rubber one day and several days later you wanted to feel the same force apply or to do something, how could you assure the forces are the same? So yeah, you have to get the same identical rubber, yeah, identical stress rubber band and state it to the same standard length. Like you should do same length. If you do it for the same length with the same rubber, identical rubber, it should be same. Do side by side rubber bands like we did with the example. Yeah, provide a convenient way of accurately reproducing forces of many different sizes. So we just did the for one. We had one with one, and then with two, with three, with four, with five. When you pull to the same standard length, it was we were able to produce forces of many different sizes. Yeah? Go ahead, write your answers and click on save and go next. Okay, do not forget to click on save and go next. Okay, after writing the answers. Okay, I think now we're going to do the real experiment. So for that one, let's do the hook. I'll have until okay, I'll have okay, let this here's the alive. Okay, I'll have I will already have the sensor in here. Yeah, can see the sensor. Okay, So since in here, then dongle. So the dongle I have already plugged in. So sorry, you may go ahead and plug in the dongle. Okay, you already know from that. Okay, let me show you. That's a dongle, yeah. So you can plug it. You see when the dongle is not there, it will go off. Okay, then you can go ahead, plug in. Okay, and then yeah. So calibrate. So you can calibrate. I hope you have this. So this is not connected for now. Our device is not connected, so we can turn it on. Yeah, turn it on. It's on. Then we can go do the calibration following these steps like we did. Yeah, like we did before. Follow these steps in here. Okay. So let's have that. Yes. Follow the steps given here. Okay. Now okay. So click save and go next. Okay, so before doing the measurement of the forces, we are asked to do the like check whether the calibration was right or not. Okay, so we'll have IOLab device. So they want us to hold it like this way. Okay, and this is zero the sensor. Okay, so click on zero sensor. Then they want us to use 60 gram. I have this water bottle which I made it to be 60 gram. Okay. Then you can click on record this in the beginning and then since it's in, you can click on record. Okay. Record and this is measure some force. Yeah. So I've already measured and then they want us to check whether it's around 0.6 Newton or not. Yeah, we have already used this tool to take the average. So kind of 0.59, yeah, we can take the 0. Around 0.6, okay. And then they want us to remove, we can remove, these are just calibration. If it is not around 0.6, there is something wrong with the calibration. You have to do the calibration, okay, you have to repeat the calibration again. Okay, click remove next to, so they want us to remove this one, so we just want the data from the rubber bands, okay. So this is done, click the record, I'll have pull 3 rubber bands to the standard length, okay. So we'll use 3 rubber bands. Let's turn the picture on. Okay, so we can use 3 rubber bands. That is being dropped. Okay. This one. Oh, I took it out actually. Let's get it back. Okay. Okay, so we can use this. You want us to use 3 rubber bands. Okay, and then pull from the parallel. Yeah, parallel, and then you can put it to the sensor. Yeah, click is for it so that it will be easy. Okay. Okay, 3 of them to begin. Okay, we have 3 of them ready to be full, and then it's always yeah. You want us to re-zero. If you want to re-zero the sensor, to make it loose, yeah, so that nothing is being pulled here. Okay, if you want to click on re-zero the sensor, but I don't think we need that. We just did that, so we can go ahead and okay. I'm not sure if you see. Okay. Okay, so what we'll do, we'll use 3 rubber bands. It says to our standard length here. So what are the standard length? 10 centimeters. So like you can have 15. If you had 15, that's also fine. So we'll use. Do you want us to record first or what? Record the average percentage reading. We could. Okay, we can do that. We can do that. While holding the present, the place proceed rubber bands to this. Okay, I can just click on record. And then we can hold it and click make it to 10 centimeter out the standard length here. 10 centimeter. Okay, I don't know if it is in time, but we can, so starting from here. Okay, it's kind of already pulling, but let me let it loose so that nothing is here. I'm not satisfied. I'm going to do it again. So now it's here. Okay, 10 centimeter kind of. Okay, leave it down to let it be. Okay, we did that one. I hope you already know about which is the area of interest, those kind of things. Let's take the second one. So this was when I was not pulling. I started to pull slowly, but this is the area for like while pulling up to the 3 hours up to the standard, it was the force. Okay. So they want us to get the average reading. We already know how to do the average. Yeah, you can click on this one, select the reason you want the average, and then you get the average value. Okay, and you can then put it down, save and go next. Do not forget to do that. Okay, after that one, this one has to do with the 2 robots. Yeah, zero the so take out the one of the robots. Okay, take out one. You can do it, but I'm just trying to show you the difference. Hey. Okay, let me take one of them out. We'll be pulling the same standard length. Okay, be careful. Now they want us to reach zero the sensor. Yeah, so this point is right here. If I show you, okay, you can put it here. Okay, zero sensor, but while zeroing, make sure there is no force being applied here. Okay, you have to lose the rubber and then only zero the sensor. Okay, and then they want us to do the same thing. Yeah, so we have to make it to the. Let's put the scale here so that you will be beautiful. So that's closing in. Then you may record. Now we have 2 rubbers. Pull it to the same 2 centimeter, 10 centimeter here, and then you can keep it straight. That was fine. And then they want us to repeat it step 11. So we have to take one out. Yeah, same thing. Take one out. I think you can do it. So this kind of instruction. Yeah. So what you can do, you will take one out. Yeah. Then you will lose like without anything being measured in the IOLab. You can reserve the sensor. Then the same thing. You pull only one to the standard length. Okay, standard after pulling to the standard length. I hope you know what is the forces. So to do the average, you can just click on that thing. Okay, and then you can select the region. I can give for both. This was the first round, second round. When you do the third one, the value will be here. Okay, so now you have 3 average values. After that, click on save and go next. Okay, I have not done for the only one number. Okay, you can do that. Okay, after that analysis time, yeah. So we have you can they want us to plot in Excel or other plotting graph force measured for versus the number of rubbers used. Okay, so you out of this which one will fit. So was it like this or like this or like this? So if there is no rubber, there is going to be no force. I think it has to start with kind of this is force. That's number of rubbers. Okay, number of rubbers force. So now when you have zero, for there should be zero. Kind of straightforward. This is so you'll plot here and find your equation. Okay. So how percent reading related to the size of the pull exerted on the force sensor hook of the rubber band. So with the if you have more rubbers, there will be more force. Yeah, we have already seen, but you go ahead make your analysis based on analysis of the graph. What sensor reading will correspond to the full of 5 rubber bands. So we did up to 3. Yeah, we were able to make an equation y equals force equals some constant slope here, some constant times number of rubber bands. So if we have 5 rubber, you will have equation based on those 3. Yeah, force equals some constant times a number of rubber bands. So when you have 5 rubber bands, you have how much will be the force. So some constant time 5 rubber bands will give you the force for 5 rubber bands. If you want for 6, you will replace this one 6 one. Okay. Okay, that was for this one. Investigation to motion and force. So we'll need 20 gram, 40 gram, 0.5 length long ramp. Okay. Okay, what's going on in this activity? So they want us to use the IOLab. Okay. We'll set up like this. Suppose you grasp the force sensor hook and move the IOLab forward and backward. Do you think that either velocity graph, the axle graph, or neither will? So they are asking which graph will look like the force graph while doing the thing. You can go ahead predict. Okay, and then actually we just did force. Did we do for force? Oh, no, we have not done. But okay, so they want us to predict which graph will look like the force graph. If we pull, there will be some force. Yeah, for velocity will be changing. So changing velocity force while pulling, there should be something. While we stop also, there will be okay. So we'll go ahead, make a prediction, and then we'll see in the so I'm just clicking save and I'm gonna X without writing. So but you must write, okay, because if you come back and write, there will be error. So go ahead, you have to feel which one is right, like predict the one, explain the prediction, and then click save and go next. Okay, if you do not fail and click on save and go next, it might be a problem. Okay, and then let's do the real experiment. So this is like similar before. Okay, you may go ahead and do the calibration thing, check whether it's done, it is right, it is like you can measure 0.6 newton or not. Okay, after that you can remove the round, we don't need that. Yeah, after you did for this one, and then click add on, and then click or grasp the force sensor hook. So zero the sensor means while zeroing the sensor, as I've already told, there should be nothing like, there should be no, sorry, it's making sound. Okay, there should be nothing here. Yeah, so nothing is being pulled here, so that has to be just, it has to be the ally only. So we can re-zero the sensor. Sensor. After that, click add on original. We can do that. So would you want us to pull IOLab towards us, so towards the positive direction by holding on this one? Okay. Oh, you're not able to see. Okay. So then you will be able to see. Okay. Now the phone is tested. Okay. That's good. Hold it. Okay. So let's do it. Okay. They want us to keep here is good thing. Okay. Pull it towards you. Then wait a second. Then give it a back. Then stop quickly. Repeat both. Okay. So let's. So then it starts and stop, and to pull and position along a straight line without lifting the lab of the tabletop. Okay. So let's click. Okay. I'll click on record. I'll hold this one. Click on record. Okay. So push like this. Pull again. Push again. Okay. So you can do as many times you push, pull towards you, stop, push back. Okay. As long as then you can do this one. It's not a thing. Okay. And then 7 go next, obviously. Yeah. Okay, so you first begin pulling the IOLab towards you first time. So when the velocity started to increase from 0, you stopped the IOLab. So when it started to decrease, yeah, kind of here, completely. Okay, you begin to push the IOLab away. So that was when we were in race, to push away means towards the negative direction. Yeah. So like we move, pull towards us with the full sensor. So then away. So you stop the IOLab as you are moving away from the first time. When did we stop? So kind of here. Okay, kind of here. Yeah. So start to go to 0. Yeah, with this process we applied the force and then it, yeah, maximum, then it is stopped. Yeah, velocity started to turn on to 0. How explain how you identified each point? So you can go ahead and explain how you identified. Okay. Okay, now they are asking, does either graph velocity or acceleration resemble the force graph? Which of them looks like the force graph? Okay. I like those, either of them is any one of them visible like the force. So you can see forces like this, velocity is like this. Yeah, but acceleration is like this. So if you see force is like here up to here. Yeah, but acceleration goes up to here. Force is like this one and goes up and come back, like this one and goes up and come back. So but velocity is kind of follow the constant. So you can make, you can see if you like from Newton's second law, you already know that, but it's still okay. F equals ma. Yeah, so based on this one, you see this is like this, and this looks similar. Yeah, this goes up and down, this comes down. So force and graph acceleration looks similar. Explain how you reach to this conclusion based on your observation. Does it appear there is a direct method? Yeah, we can see there is, if they are kind of scaling only. Yeah, scaling only, they look similar. If only there is, you see the brains or the scale like the scale they have been measured is range, so they have this force and acceleration seems to have mathematical relationship. So you may go ahead, write your answers. Okay, write your answers and then only click save. And I'm just giving instructions, so I'm just clicking right now. But you have to write the answers and then only do this one. Click on, okay. Okay, and then it's prediction time. So it's, I think we already speeding up again. So you have seen the previous area, the force and so force and acceleration seems to be related. Yeah. So if we have this kind of force, acceleration is also similar. So you have a positive acceleration here. So if you remember from previous labs, you should be able to do the idea. Acceleration is positive. So that can be speeding up. Okay, one is by speeding up, gives the same, speeding up in a direction gives the same direction of acceleration. Yeah, it's same direction to the say of like same speeding up in a direction gives a same sign to the acceleration of that direction. So if it is speeding up in positive direction, acceleration will be positive. Speeding up in negative, acceleration will be negative. But for slowing down, it will be opposite. Slowing down positive will give negative acceleration. Slowing down in negative direction will give positive acceleration. Okay. Slowing down negative will give positive acceleration. Slowing down in positive direction will give negative acceleration. Okay, so positive acceleration. So it's speeding up. If it is speeding up, to get the positive acceleration, it has to be speeding up in, so velocity has to be increasing with constant velocity. It is a constant, yeah, velocity has to be increasing with constant length. So make your prediction. Okay, in this one velocity is constant, it cannot be true. Yeah, so we cannot have acceleration. Velocity, like acceleration is constant, so it should be linear constant slope. It can be, but they can this be speeding up in negative, so it will give negative. It cannot be, so same way. Okay, go ahead, make your prediction. It is slowing down in negative, but it is not giving a constant acceleration. Okay, make a prediction and write the answers. Don't forget that one. So then go next. Same thing for the acceleration. We just explained. Yeah, already explained. Force and acceleration are related. So based on the this force, which one you will get the acceleration for? They have to be directly. If that's positive, that's positive. Same force, a positive acceleration is up. So positive, yeah, same thing. Go ahead, make the prediction. Do not forget to write your answer. Okay, I'm just clicking save and go next, since it is just instructional video, so I'm not writing everything down. So but make sure you have to write that down. Okay, okay, speaking up again. So this mass is right. Okay, so we need to set up like this, splitting up again. Okay, so we have a like our card, force sensor is towards this side. Okay, force sensor, so this is moving positive direction will be like that. So it's better to have this round here. Okay, so that force will not be decreased when you, and it's to start will use 20 gram. Okay, hanging from it. So and then this is regular what's that called, calibration thing. If it doesn't happen to be 0.6 Newton while doing calibration, you have to mm, recalibrate the force sensor. Okay, IOLab, force sensor of the IOLab. Okay, due to inactivity, it has gone off. So let me turn on the IOLab. Okay, so I have made a setup like this figure. Yeah, so this is a force sensor pointing double towards the single wheel positive direction. Yeah, it's force sensor okay here. I have this string here. Okay, I played 20 gram weight with the whatever. You can use the real weight also. Okay, so I will click. Okay, so this the calibration you can do it. Okay, so you can do the calibration measure 0.6 Newton already, and then remove the round for that 0.6 Newton thing, and then okay, the first sensor by clicking this. So while it is there are nothing should be pulling it. Okay, so like the you can let the string loose, and then nothing should be done. You can click on there is a sensor, which is the sensor. Okay, so this nothing is pulling. There is a sensor. Okay, after that they want us to yeah. So it's better to have this not this is okay, because it cannot create the friction, so that it can be pulled by the force that we have used directly applied to it. So we can put it like this. We want just to restore it, yeah, and leave it after some seconds. So I left it a little bit long, so let me do it again. That's fine. So that's not that too much bad, but it hit the ground. So I just okay. Yeah, you can add one. Record it, and then you can maybe I just tell before you put the okay. That has to be good. Okay. Okay. Yes, after that, just it here. And this is a new. Okay. And then we put this first one and this one. Okay. So our area of interest is as of now right now. This is the one. So that's where when it was speeding up. Okay. So you may go ahead and select it like you can use this one. Just do it from beginning, but after that point we can select. Okay, that should be good. Yeah. Okay. And it also, this is when we were just following the IOLab, so it's like that's it. Okay, and then this is the review, the acceleration is the most important. And so you can click on 7 okay, now we have to do the analysis thing at the time interval before the mass is erased. So before the mass, so we scale it out, but if we start from zero, yeah. So the round in the velocity has started to begin. It was kind of it was for release, yeah. We didn't release our like one for this and before the velocity. That moment when it is zero, when we started to increase from zero, time interval means we have to give it the range. The moment you stop the IOLab at the edge of the table, so that's when you stop there. Okay, and the average force only, including the time interval during the IOLab was being pulled. Okay, so being pulled by the force falling mass. So don't get confused here. They want you to do the force average, but not for the whole region. Just the region from here to here. It's kind of constant there. So you just have to do it from here. You can auto scale if you feel you need that. Okay, or you can increase the graph also. Anything. Okay. No, that's not a good choice. Oh, because based on the value, it auto scale. Yeah, it's wrong. So we can just use one. One. Okay. Or you can use your average choice. Okay. Then do the average. To do the average, you can just use this one and be clear about the reason they were asking. Just when the IOLab was being pulled by the mass there. Okay. Then you can write the answers. I'm not writing it, but you have to write it. Okay. Do not click save and go next before writing. It will be a problem. So save and go next, and then it's more of analysis. Yeah. So after the card is moving, the force that is applied to the IOLab, whether it's constant or what happens. So when the card is moving, the force is kind of constant. Yeah. It's a law, but you can see it's kind of a straight line. So that's when graph. Now, how does the acceleration vary in time? So while moving, so that is how does it look? Kind of constant again. Yeah. Whether constant force applied to the IOLab produces a constant acceleration. Constant force was being applied is the acceleration constant. How does the velocity vary in time? So this, what is this? It's a that does this agree with the prediction? So go ahead, based on these write your answers, okay? I'm not writing everything as this is the instructional video, so I need to learn the things. Okay, you click on save and go next. So what are we doing? Okay, acceleration from different forces. So since force is proportional to accelerations from like so we cannot say it right now, but it is related to the acceleration somehow from the experiments that we have so far done so far. So based on that, you have to make the prediction. Okay, so if the force is twice large, how will it, what would happen to the acceleration? Will it be unchanged? Will it be half? Will it be doubled? None of the so based on the whatever we have done up to this one, you may go ahead and do the prediction. Okay. Okay. Now we'll do the same thing, but with the higher mass. Yeah, higher mass. Okay. So you can. Okay, everything is same except the mass. Yeah. Now we'll be using 2 times large. So we'll be using around 40 grams, which I made in the water bottle as well. Okay, 40 grams. So you can do the regular 60-gram thing, calibration thing, and after you do that, you can remove the one for this calibration thing. Okay, if you don't get 0.6 Newton force while measuring with the secure, like measuring 60 gram, as explained here, you need to recalibrate your force sense. Okay, going to calibration here and force. Okay, you need to do that if you sorry if you don't get 0.6 here. After that, insert the graph. We did that. There are the force sensor. So while you're in this, it should not be pulled. You have to let it string loose. Okay. This okay. And you can click on the sensor. Okay. And then rest of the like the experiment is similar, or like what we have done before. Okay. So let's hang it up with the 40-gram mass. So what do you expect? That more force is being pulled, constant, more constant force. Yeah. I like being it here. Let me click on record. Okay, and then just leave it. Okay, good. And look good, but let me do the second one also. It's kind of good. But I had a bump at the end, but that's okay. And run. Record. Immediately release it and catch it before it hits the ground. Okay, do it later. Kind of okay. Okay, put it down. Let's go to the analysis part. Okay, and then again, I didn't need the second one. Okay, you can do as many run as you need, so it's not that problem. Okay. Okay, and then we can select our region of interest like before here. So we can just click on this one. And go ahead and let's see the website to see. So that one there would be okay. Yeah, kind of your IOLab was moving. Okay, and then okay, so you can click save and go next. After that, you can like make your selection of region. Okay, same thing like we did before, the time before I before the mass was released. So don't put it 0.8 on, like hold 0 to 0.8 seconds. Yeah, so exact moment it's released. So when you start it greater than 0, in the moment you stop the IOLab, similar. Yeah, and then you stop the IOLab is right around here. Yeah, measure the average acceleration during the same interval as the average force. The average force during the time interval, so it should be here. Average force during the acceleration, sorry, acceleration has to be here. Okay, how did the force compare to the activity 2? So you may go ahead and compare. I have not written the answers in this plan. Activity 2 was kind of here. Yeah, so you can go ahead and compare the force here. Yeah, this is our area of moving, so it's kind of here only. So you may go ahead and compare the value with the average. Yeah? Well, I hope you know how to do the average. We have been doing that. So you have to click this one, select the area. So don't go beyond this, go beyond this. Okay, just be with the, while doing average, while moving the IOLab, be within, like you can do from here to here only, just in between. But if you want to do the whole thing, you can be, don't go beyond this one. You see, it is going to be down. So you have to just up to around 1.7 is the perfect, like 1.67 is the perfect, but you can do up to here also. That would be, since it is constant. So go ahead, write the answers. How did the force applied compared to the smaller mass in activity 2? How did the acceleration of the car compare to the car by? Okay, so you can compare this one. Make sure you write the answers and then save and go next. Okay. Okay, it is the same thing. Okay, you have to follow the same process. You will do the 60 gram and do calibration. Yeah, and same thing, similar process like we did for 20 gram, 40 gram. You will do the same thing. Okay, so you're trying, you'll be expecting a higher force here, yeah, a little bit higher, same nature. The graph of the natures will be same. The nature of the graphs will be same. Okay, sorry, the nature of the graphs will be same. Only thing is like if you have higher mass, the slope would get higher, the value of the acceleration would get higher, the value of the force would get higher. Okay, so you may go ahead, do the experiment. Okay, for now, I'm just clicking record, stopping, just to click save and go next. Okay, you have to do and then only click on save and on. So what they want is, yeah, they want you to plot now. So you put your average values and average acceleration. Okay, so and it should have a relation like F equals ma, but do the thing, plot it, and you'll see the relationship. Okay, and comment on the mathematical relationship. If you increase the, put it in the plot, find the relation. Okay, if you increase the force applied by a factor of 10, so after you had the relation, you should be able to see, like from our experiment also, you will be able to see when you have one, when you have, like if you have force 1, some acceleration is zero. If you double the force, acceleration is also doubled. Okay, so similarly, if it is factor of 10, how you can go ahead after you have the equation, it will be more clear. Okay, same thing. How the velocity time. So acceleration magnitude is going to be, so what will of the velocity time graph change there? Rate of change of acceleration. So slope has to be 10 times. Okay, so go ahead, you can do the analysis, write your answers. Don't forget to write. I'm just clicking. Okay, you can save and go next. and then after everything is done you can go here. Yeah, the report will be created. Oh sorry, we're writing in, but yeah, you have to, this is export, but you have to edit. You can write your name and you will say some comment. Okay, and you will save that one and to save it as PDF. You will convert to export to PDF and save it in required location. Okay, thank you for your time. So, experiment.